Hello, my name is Derek from Tomcat Gas Training, and this series of videos you're about to undertake is all about gas controls. So we're going to be looking at all the different types of gas appliances and all the different safety controls what are used on each appliance. The first appliance we're going to be looking at is a gas cooker. So let's have a look at the controls we can find on a gas cooker. Well, first thing we're going to look at is if a cooker has a glass lid and what safety device we're looking for to protect this glass lid. Now, the glass lid is basically a decorative part of the cooker, okay? But, as the name says, it's made of glass. So, the glass is not shatterproof, okay? So the heat from the rings could actually shatter the glass. If the glass is missing or the glass is broken when you go to service a gas cooker and the safety device has not been made inoperative, then the appliance needs to be notified to have the lid replaced. But if the customer is using something to keep the safety device open to allow the gas through to the hobs, then that would be classed as ID in the unsafe situations procedure IGMG 11. So the way we test it is pick the smallest ring at the front and turn it on. So this is my smallest ring at the front. Now, I don't know whether this glass lid works or not, so what I always do is just turn it down a little bit. Don't want it on full burn because I don't know whether this works. And then I'm going to slowly lower. Okay, we can see it's gone off. Okay, so what I can do now is I can turn it on fully, knowing now when I shut the gas lid it shuts off and I can see it's gone out. Okay, now what I can do is I need to test all of them, and now dropping the lid down and we can see all four go out. Turn it back on and I can see they're all back on, they're all working, and everything's tickety-boo. Next one we're going to look at while we're here, it's a control, not a safety device, it's a control, is the gas tap. So basically, we turn it on, okay, and it's giving us a good flame picture. We now turn it to minimum, make sure it doesn't go out, and we can see now that that hasn't gone out. We can now turn it back up and turn it off, okay. So that's just something as simple as checking whether the gas tap's stiff or not working, not turning off. The next safety device I'm going to look at is the thermoelectric device. Now, the oven we've just looked at doesn't have any thermocouples on the hob itself, sorry. So the thermoelectric is made up basically of two parts. We've got the thermocouple, which has two dissimilar metals with heat put together onto those two dissimilar metals will make about 14 millivolts of electricity, which Thomas Seebeck found out. What that does is it opens an electron magnet. So the part of the safety device we're checking is the thermocouple lights and stays lit, and that's creating that electric to actually keep the thermoelectric open. So I've got to hold the knob down to override the safety control. So I'm overriding the thermoelectric part, the electron magnet. Now the thermocouple's heated up by the gas. It's now made that 18 millivolts of electricity, which is now keeping the magnet open. Now when I blow this out, it has a time to knock off that that electron magnet. On the old cookers, on the whole hob, it was 90 seconds. It's now 60 seconds for all, unless the manufacturer tells you anything different. Normally what you would do is turn it down to minimum and blow it out. I'm going to blow it out on maximum so you can kind of hear the gas coming out. So you can hear that gas coming out. I would now start my stopwatch. And that knocked off in just under 10 seconds. Okay, now I can't hear any gas coming out of there, and if I press the button down and light it, I can see it's not passing. That is completely shutting off because I can't hear any gas coming out, can't smell any gas coming out, and the igniter's not igniting anything. So we can pretty much say that's correct and works. So we'd have to do that now for all the others. So I've tested all those. we can see there's no gas coming out, I can hear there's no gas coming out, I can smell there's no gas coming out. So we can say the thermoelectric devices on this hob are working. The electron magnet is also working and sealing off. So everything's tickety-boo. Now the next thing we're going to look at is the actual oven burner in a cooker. Now there are two types of burners, well not burners but the flame supervision devices. There is one which is called a liquid expansion or liquid vapor valve, and one which is worked off the thermoelectrics. So the first one we're going to be looking at is the liquid vapor valve. So let's have a look now. Now this cooker has the liquid expansion or the mercury vapor valve in there. So the older, really old ones had mercury in, the newer, older ones had alcohol in them. So to light the oven, what we need to do is we need to press the oven knob in, because we're overriding a safety device, so we've got to press the knob in and then we can light it. So this oven has to light in low rate. If it lights in high rate, that means the liquid expansion or the mercury vapor valve is stuck in the open position, and that would automatically make this oven ID because a safety device is not working. Then it goes up to high fire. So I now know that this burner has lit in low rate, it's expanded the file inside there with the alcohol or the mercury in there, which has now opened a set of bellows and the gas valve and allowed the gas to go in full burn. Now when we press the button in, we allowed gas through what's called the bypass rate. Now the bypass is actually kind of the pilot light. When we press the button in, the gas goes down the pilot, that's what lights, then that heats up the file, which then opens the main gas valve, which allows the gas in. Now I'm going to test and see whether the bypass is still working, and I'm also going to test the actual mechanical thermostat in this oven is working correctly as well. So I'm going to close the door and I'm going to turn the main oven onto slow cook or simmer. And what's going to happen now is the thermostat inside the oven is going to now work, and that's also a file which also has alcohol in there, which also affects the valve. So it will expand and it will close the gas off to the valve. So it will reduce it back down, should do, to the bypass rate. Now, if it goes out, when it goes down in temperature and shuts off the main burner, that means the bypass is blocked. If it doesn't go down at all, then that tells us the mechanical thermostat's broken. So we're kind of doing 3 tests in a very short space of time on this oven burner. And it now sounds like it's gone off. Okay, so it should, when we open this door, still be lit, but in a very, very low flame. And it is. So that means the liquid vapor valve's working, the bypass is working, thermostat has taken it down to the bypass rate. I'm just now waiting for it to go back up to full fire again because all the heat's coming out of the oven, and again that tells me the mechanical thermostat is working correctly. The last check I'm going to do now is I'm going to, now it's in low rate the burner, I'm going to blow the flame out, and what should happen now is the liquid vapor should cool back into a liquid and then knock off the main gas valve. So we should hear the gas valve try to go into high rate because it'll think the temperature's changed. It will then realise via the vapor part of it that the heat is gone there now, and it should knock off the main burner. But the only problem with these is it still leaves the bypass leaking gas out. So it's on low rate. Should hear the gas come up. It's now knocked off and it's lit in the bypass rate. It's now gone back up to full burn. So that's the final check for this. Now, the flame supervision device in this oven burner is thermoelectric rather than liquid vapor. So the tests for that are pretty much the same. So I'm going to turn it all the way on to maximum. I'm pressing the button in now and you can hear the gas coming out. But this time the oven lights in high rate rather than low rate. Now what I'm going to do now is I'm going to turn it down to simmer again so you can see it's in high rate. I need to close the door. So as a gas engineer, one of the first things you need to do really is find out before you start working on the oven itself, is it a liquid vapor? Is it an old liquid vapor? Or is it one of the new thermoelectric ones? Even when a gas engineer is taking his reassessment or it's a new guy taking his initial assessment, my advice would always be before you start working on that cooker, when you're doing your visuals, have a look and see what safety device it does have. Okay, it's nearly gone all the way down now, so I know the mechanical thermostat is working. So what I'm going to do now is I'm going to blow it out. Hopefully we're going to hear this click, and this click has to be within 60 seconds. Once the click has happened, I'm going to try and light it. It shouldn't light because the thermoelectric should knock it off completely. There you go, you heard the click. So if I try and light it now, it shouldn't light, and it isn't doing. So I know the thermoelectric has knocked off, but we got pretty close. I don't know exactly how long, I think it was about 30-35 seconds. So we were still well in with the 60 seconds. So that's how you test the thermoelectric device on the oven burner. Next, we're going to have a look at the safety devices on grills. Again, two types of grills. This is the high level grill, and then we've got the low level grills. So let's have a look at the high level grill first. Now this grill has a thermoelectric device in it. So again, I've got to press the knob in, press the igniter to light it, leave it for a few seconds, let my finger out, and now it's controlled by the gas tap on the front, so I can have it on high or I can have it on low. Okay, there's no temperature control on this, it's just basically more gas or less gas. But it is, the safety device on this one is actually the thermoelectric device. This high level grill only has ignition. It doesn't have any kind of safety devices whatsoever, but still you control it on high and low by the use of the gas tap on the front. There are no thermostats in this at all. This low level grill is slightly different. The burner is slightly different, but again there's only ignition down this end. There is no safety devices, and the only way of controlling the heat is via this knob. So high and low. Now the main control or the main safety device you're going to find on a modern gas fire is this here. Now all fires now have what's called ASDs, atmospheric sensor devices. It's also known as an ODS, which is an oxygen depletion system. So it kind of has two words, but the ASD is made up again of two parts. Working off basically a thermocouple. So your thermoelectric device, which we looked at in the cookers very closely, this is also what is controlling the flame supervision device, the FSD, on this fire. Okay, so this fire's safety devices are an ASD working with a thermoelectric. Okay, so it's FSD, its flame supervision device is an ASD working with a thermoelectric. So how does it work? So it works like a standard thermoelectric. Again, so if I light it, so I'm going to press the knob down. So because I'm pressing the knob down here, you can see I'm pressing it down. I'm overriding the thermoelectric device. This is the thermoelectric device here, which is connected to the thermocouple. and the thermocouple is here. So this is the ignition, this is the thermocouple, and then we'll look at this part more closely. This is your ASD. So as I press down the thermoelectric, I'm overriding the safety device. It now turns on to pilot. You now hear the ignition. So it'll click twice because it gives you 2 attempts. We're now going to hold it down for 10 seconds. So the thermoelectric device, so the thermocouple creates that 12 to 30 millivolts DC, which then holds open the thermoelectric device, which will then allow the gas to these 2 burners. Okay, so I can now spin the knob and all 4 radiants will now heat. So this is what we call a duplex burner. So there's 2 burners here. So basically what one of these injectors does is put gas to the middle 2, and the other injector puts gas to the end 2 radiants. So basically you can either have it on low and high. That's how this one works, on low and high, through a duplex burner. Anyway, so what this has done now, it's heated the pilot flame, it's heated the thermocouple, the thermocouple's created that electric. We've then pressed down the thermoelectric. It's now keeping the thermoelectric magnet on, so it's allowing the gas through to the burner. We've now turned the knob, which has now allowed the gas to come through. Okay, so if I blow this pilot light out, the thermoelectric again, well, the thermocouple will cool down, cease making the electric, and the thermoelectric device will knock out, as it did on the hobs. But on this one, even though we now say everyone's 60 seconds, in the manufacturer's instructions for this one, it's 180 seconds. So let's do that test first. Let's blow out the pilot flame. Let's put it on to pilot, otherwise it'll just keep relighting. So I've just got it on pilot now. I'm now going to blow it out and we'll time how long it takes for it to knock out. Are we ready? You hear that click then? So it's well within that 180 seconds, okay, which the manufacturer said way back. Now that's the first part of this safety device. So if the gas ran out, it would knock off the flame. But the ASD part of it is, so this is basically made up here of 2 parts. So when I light it, now you can see it's actually burning in 2 directions. This is called a ribbon burner. So basically the gas is coming through this pipe here, into here, okay? This is a lint arrestor here, and this lint arrestor is protecting the air relief inside the air hole inside here, where the pre-air comes in for combustion to mix with the gas to make the pilot flame. So this is your pre-air, this is your post-air. So it's now bending and bend in towards the burner, but it's also burning horizontally into the tip of the thermoelectric. So the top 7 mil or so in there, so it's probably less than that. Now then, if I drop down the lint arrestor, there is a hole where the air comes in. If I block that hole off, you can see we've now got incomplete combustion, and the flame has actually lifted off the thermocouple. So what can happen in this situation now is the thermocouple will cool down. That will then knock off the gas going to the pilot, okay? Now, this normally does take about 180 seconds, and by that time my finger's fallen off. Let's just see how long it actually does take to knock off. That is how you test the ASD. Now let's check the safety devices for this Inset live fuel effect fire. Let's see what the differences are between this fire and the radiant fire we just looked at. Now again, you can see this type of fire has another ribbon burner. So this has an ASD. So if it has this ribbon burner here, like we saw on the radiant fire, then it will have an ASD. Without that ribbon burner, it can't have an ASD. Okay, so again, you can see it's going into the thermocouple. So this time, the knob here, that's off. When we press it here in, we need to press it in again. And then we need to press the ignition. So you can see it sparking there across the igniter and across the thermocouple. Then once it's lit, we can then turn it to large flame and small flame. Okay, so again, if we flip it over, you can see thermoelectric device here. You can see again the gas valve is directly in line with the thermoelectric. Again, you can see the thermocouple lead. This is your ignition, so this is a manual ignition. Some fires have, when you press the knob down, it automatically ignites and twists like it did on the radiant fire. Again, this is our inlet side for the gas. This is then going off to the burner, and you can see then that's where the pipe goes to the burner. So this has got this exactly the same device as the radiant fire, even though this is an Inset live fuel effect fire. Now there are some Inset ones which have the controls on the side here, but again they work exactly the same way as this one does and the radiant fire. So basically the safety controls we've got on here, on any gas fire really, are the thermoelectric from the thermocouple, and the ASD, the atmospheric sensing device, and the controls it has are the control knob. Now this is a fan flued gas fire. So the firebox itself pretty much looks the same as any open flued Inset live fuel effect fire, except a couple of differences. First one is, it's got a plug connected to it. So I'll plug this in. The next thing it has this box on the back. So this is the cover, what you would see on the outside wall, so there's no chimney needed. And if you look inside this more closely, you will see that it's actually the fan off a boiler. There's also an air pressure switch in there. So they're new controls. When we'll look at those controls when we look at the boilers. So inside here there is an air pressure switch and a fan. Here we have a little control box. So when I press this control box to on, the light comes on and the fan opens up and starts to run. Now, what that activates is actually on the fire, this is a solenoid valve. So it's using electricity, an electric solenoid valve to open and close the gas. Now the reason why it has an air pressure switch in there is because it's fan flue, and the fire and the flue are connected with this pipe. So without the air pressure switch, the actual fire wouldn't know the fan's running. So the air pressure switch is the safety device. So that's telling the little PCB inside this control box here that the fan is running. And because the fan is running, the fire can then go into its sequence of operation. The fire itself lights just like a normal live Inset fuel effect fire, and it has an ASD, a thermoelectric device built into it. But it just has this solenoid valve to open and close the gas if the fan is not on. So you need to turn the fan on first, then you can light the pilot light, then you can turn it on. And if anything happens with the fan, operates that solenoid valve and turns off the gas supply. Let's have a look at this solenoid valve more closely. So this is a solenoid valve. So basically a solenoid valve is an electrically operated on-off valve. So when electric current passes through a coil, so this is where the electric current comes through here, and this is the coil here, it produces a magnetic field and an armature which has a valve attached in place inside this coil. When the coil is energized, the armature is drawn up the coil and the valve is lifted off its seating. Now this can either be AC or DC in here. Now this is actually an AC coil. Biggest problem we have with AC coils is they get incredibly hot and they can shatter. Whereas DC coil, because the voltage is lower, gives off less heat on the top here and doesn't make any kind of vibrating noise. So let's get these bolts undone and let's have a look inside here so we can see how it works. Now you can see I've removed the bolts from around the flange. So if we take the coil off the top, you can see this part here is the armature. Now what happens is the armature gets sucked up by the electric. Okay, now on a lot of these, the spring, there's a spring here. Okay, so most solenoid valves have a spring, so when it does get sucked up, it puts pressure on it, and then as the electric is broken or the spring then returns it back. But this one's slightly different, because what the spring is, so if I can get this attached back to where it goes, so that goes there. On this one, the spring is at this end. Okay, so it gets sucked up like that and helps to pull the diaphragm up. Okay, so this diaphragm gets pulled up by the spring, okay, being held together. The gas then comes in through here and has to go down here to be able to come out of this pit here where it says out. You can see this is the seats here, which seats on this. This is raised. I don't know if you can see that, but it's actually a raised face there. So that washer, this rubber washer, is sitting inside here. So when you turn the power on, it pulls up, and if you look here, I don't know whether you can see, there's a hole all the way through it. So that does differential in the pressure. So as this pulls up, there is another rubber washer there. So the spring stays attached, pulls it up, opens the valve there, which helps differential the pressure, then the gas can go down. So this is how this solenoid valve works. Now this solenoid valve we use here on our emergency stop buttons, but the ones you would probably find in a boiler would have a spring in the end here, which when it gets sucked up, okay, the power gets energized. When the power is de-energized, the spring overcomes and pushes it back. This is what we call a normally closed valve, and there are also normally open ones. Okay, when you normally open the normally open ones, when you put the power onto the coil, it closes the valve rather than opening it. So that's a look inside this AC solenoid valve. First boiler control I want to look at is back in time. Let's go back in time when I was a lad. Multifunctional gas valve. Now then, boilers don't have multifunctional gas valves anymore. They have what's called zero governors. We're going to look at those later in condensing boilers. But the old type boilers, the atmospheric burners, so this is an atmospheric burner here, they needed a multifunctional control valve. So the components for this multifunctional control valve are gas isolation valve. So every gas appliance requires a gas isolation valve. Next thing we come into here, which is this grey button, the grey push button, which is the gas control cock. What it does is, again, when we push it in, we're overriding the thermoelectric device, and the thermoelectric device is here at the back, and you can see the thermocouple going down here. So again, when we press in the button, we're overriding the safety device. We can now use igniter, the piezo, to light it. We can hold the grey push button in for 10 seconds or so. We can pull it out and we've now got a pilot. Next part, we go from the thermoelectric device, we go into the regulator or the governor, where we can adjust the pressures. The old boilers were what called range rated. Range rated meaning we normally had high, medium and low settings where we could set the burner pressure, and setting the burner pressure would set the gas rate. So the higher the burner pressure, the higher the gas rate, the more kilowatts the boiler was giving out. Okay, we'll have a look at that in a minute. We then went to a solenoid valve, and the solenoid valve is operated by an electrical thermostat, and this is the electrical thermostat here. Now, unlike a cooker where it's mechanical thermostat, this is actually connected to the electrical supply here. So first of all, I've got to make sure my control knob is turned off, and I can now turn my power on. So I've got my thermocouple lit. So what I can do now is, when I turn my electrical thermostat on, you'll hear a click, which is the solenoid valve, and you can now see the gas burner is lit. Now the gas comes in at this end here. So this gap here is where the air comes in for combustion. It then, your 50% pre-air, mixes with the gas. It lights at this end and burns back to the injector. So basically this is the boiler knows it's completely lit because there's no control for this. The only control is the thermocouple. If you got an explosive ignition on this, normally what it would be the thermocouple flame would be tiny and wouldn't be enough to light it, so we get a build-up of gas and we get explosive mixture. Now if you did have a small pilot flame, one of the things you can do is use this adjuster here to increase it. If I screw it to the left, you should see the flame increases, and if I screw it inwards, you should see the flame decrease. So that is your pilot adjuster. Again, if I blow that thermocouple out, I've got within 60 seconds for it to click out. But this is off a back boiler, and a lot of the old floor standing open fluid boilers, you couldn't blow the pilot flame out. So on the control cock, basically what we could do is we could turn it. So we could turn it clockwise and the pilot would go out. Now we would start the timer and we would be waiting for the click, but no, I can't push the button back in until this click has happened. There you go. We can now press the grey button in and the pilot flame lights again. The other thing is, once we've checked the thermoelectric, we need to see whether it's passing or not. So with a cooker, you can normally hear it and smell it. With a fire, it's pretty much the same. And you could use a naked flame then to see if it is actually passing the thermoelectric. Now, we need to test and see whether our thermoelectric device is actually passing. So the way we do it is, first of all, what we need to do is, I need to level and zero my digital manometer. So I've done that. And I have an inlet test point here. So I can now open the inlet test point. And I can now connect my hose onto the inlet test point. So I have now got an inlet pressure of 23.7 millibars. Well, that's with the pilot going. Now, what I'm going to do is, I'm going to blow out the pilot flame, and when I hear the click, I'm going to turn off the gas supply. And what that's going to do is, it's going to trap the gas within the multifunctional gas valve and not allow gas in. So if there is a leak on the thermoelectric, our pressure should start dropping on the gauge. So first of all, I'm going to blow out the pilot flame. And now once I've got the click, I'm going to turn off my gas supply, but I'm not going to turn it off until I hear the click. Okay, so the thermoelectric's kicked in. I'm now going to see if this drops down, and at the moment it's reading 24.1. But it's not going down. So that means the gas what's trapped within the multifunctional valve is not leaking through the thermoelectric device. So that proves the thermoelectric device has slammed shut. When you heard that click, it turned off and it's not passing through the pilot flame. Now, the last safety device control I want to look at on a back boiler is this thing. And this is what's called the sniffer tube. So basically what this does is, the air for combustion from a back boiler comes from the front of the unit and then it gets drawn in through the burner. But also what it does is, because the draft diverter is here, the air also gets drawn in to dilute the products of combustion and to aid the fluid flow. Now what they've done is they put the sniffer tube into the hood of the draft diverter. Okay, so it draws its air for combustion from the ASD from the hood of the back boiler. So if the hood got vitiated, so we had downdraft, we had incomplete combustion, then this would get vitiated. It then wouldn't supply enough oxygen to the ASD and would knock out. So this is actually an ODS, an oxygen depletion system. So this is a sniffer tube, and the way you would test that would be with the appliance running, you would stick your finger over the sniffer tube and it would knock your pilot off, which would make your thermoelectric cool down, which again would knock off your thermoelectric. So let's have a look and see how this electrical thermostat works. Now this is what it looks like inside this electrical thermostat. So basically what you can see here is where the live wires come in. So this is where your live supply comes, then your neutral, then your earth. So this is your power supply coming in. Now this black wire you can see coming off here, this is what attaches to the solenoid valve. So this is one side of the solenoid valve, okay, because this is a 230 volts, we need a live and we need a neutral. But if you can see how it's been wired, basically when the live comes in, it's going through this switch here, and this is the control knob on the front. So basically we're only switching the live wire to the solenoid valve. This is the temperature file, which is connected on above the switch, so that also breaks the live supply. So the neutral is going straight to the solenoid valve, the earth is going to the solenoid valve, okay, but the live is always switching. So that's all it looks like on the inside. So basically when this does operate, you're only switching the live wire, not the neutral. So let's have a look and see this in action. Let's see it working in action. So first of all, I'm going to turn it on. So now I've got to turn it on. And now we've got here, this is the file, pretty much the same what's in a liquid vapor, pretty much what's same in a mechanical thermostat. It's filled with alcohol. So I'm just going to put this over the flame here. Once it gets up to temperature, it will knock off, but this would actually be installed in the water side, in a dry pocket. So this would be detecting the water temperature, not the flame temperature. But I am going to use the flame temperature to simulate it. So what should happen now is it should get up to temperature and it should knock the gas supply off. Straight away it's knocked it off. So if I move this away from the gas supply now, I'm not touching the thermostat, and what should happen now is that should cool down and the burner should come back on. Pilot flame still on. So as soon as that cools down, as soon as it goes back into a liquid rather than vapor, there you go, it's back on. And you can see it's automatically brought on. But remember, this would be in the water side, not in the flame side. There's no control for the flame side, only your burner pressure. Let's have a look at the burner pressure. Now what I've done is I've connected another digital manometer onto the test point where we would take burner pressure. So we've got our inlet pressure of 23.6 millibars, and we've got a burner pressure, well, it's reading 0.2, but that's just because I put it on. Now then, when I turn it on, that should change. Now I've got this set to around about 3 millibars, so let's see what it goes up to. 3.1, 3.1, 3.2, it's flickering through. So what's that doing now is that's picking up my burner pressure. Now, if I wanted to adjust that burner pressure, what I would have to do is, first of all, I would have to take the dust cap off the front of the regulator. Now, if I screw the regulator in, my pressure should go up on my gauge and the flame should rise. So what I'm going to do is I'm going to give it quarter of a turn. And what I've done now is you can see the flame's gone higher and it's actually gone up to 5.8 millibars. Now if I turn it back quarter of a turn, we should get back to this 3 millibars. So I'm screwing it anti-clockwise now, and that will reduce the gas going in. So it's now reading 3.4, just need to go a little bit more. 3.3, only tiny little turns. 3.1, back where we were when we started. So if I screw the regulator in, it increases the gas flow, so it gives you more gas going through to the burner, which would increase your gas rate. Okay, and if I screw it to the left, so anti-clockwise, that would then decrease the pressure on the spring, which would decrease my gas flow, which would decrease my kilowatts. Now the next control or safety device we're going to be looking at on boilers is flame rectification. Basically what flame rectification is a way of the boiler knowing that the burner is lit. Now this is the burner, and this we can see down this side is ignition. And if we come across the other side of the burner, this is the flame rectification. So what's going to happen is the burner is going to ignite here, work all the way across here, make rectification here, which is going to allow the gas valve to open fully. The first thing we're going to do is we're going to turn the boiler on. So we've got it all ready and we're going to call for heat. So when we call for heat, you probably won't hear the pump come on, but the pump will be the first thing to come on. Then the fan will come on. So that's the fan. You'll hear the air pressure switch click, and we'll come down to ignition. You'll hear ignition, it'll light across the burner, you'll get flame rectification, and the boiler will continue. So turn it on. That's now got flame rectification and is keeping the boiler going. So how does this flame rectification work? Well, basically it utilises the burner flame together with this suitable electrode. The electrode's at the back there, I don't know whether you can see it. And what it does is it gives a half wave rectifier to this small AC current. So the flame acts as a conductor and turns the AC current into a DC current, which goes back to the control box via an earth return, and this confirms the flame is alight. So this sensor is made of stainless steel and porcelain, which makes the current of between 1 and 7 microamps DC. So this current then energizes a relay in the control box, which opens a gas valve. If the sensor is broken, it's corroded, or it's covered by carbon, it will not sense the flame and it won't return this DC current, and the boiler will shut down. Now, what I'm going to do now is I'm just going to turn off the gas at the bottom here. So I've isolated it to the appliance. So this is going to test now whether it locks out, because this is what it should do if it doesn't sense the flame within 5 seconds. So I'm going to go turn it back on again. So it's trying to ignite. It's now locked out the boiler, and now put a fault code on of F1, and if we looked at the manufacturer's instructions that would say no gas. So what we'd have to do, turn the gas back on, reset the boiler, turn it back on, and it should ignite now. So what's that to do is purge the burner of any unburnt gas, and away it goes. So that's how you test flame rectification. Now, testing these probes is incredibly easy. So what we've got here on this side, this is our flame rectification, this is our ignition. Okay, what I've got here is a multimeter. I've got it set to audible buzzer, so if I put them two together, you can see it buzzes and it changes the screen. So if I go on to here, which is where the cable will be connected, and I go on there, you can see I've got a buzz and I've got continuity. If I go to the end and press it, I haven't got it, because this is full of carbon. So if I go down this end, you can see I've got continuity there, but as I go down the probe, you can see there's no continuity. So this would not be picking up the flame because it's full of carbon. And to get rid of that carbon, what you would have to do is you'd have to use a file and file it off rather than wire wool, because you'd never get it off. So sometimes you can get a break here as well, but you can see I've got continuity there, go around the corner, got continuity. See where it starts going a different colour, start losing, and I've got no continuity now, so this wouldn't work. Okay, and the ignition is pretty much the same. So if I go on here, I've got continuity here, but if I start going near the end, I haven't got it. So what this would be doing is trying to spark, instead of on the tip here and sparking across here, it would be sparking where we get continuity. So it would be starting to spark here, and again we could get explosive ignition. Always check on a service if you've got these, and even on the new condensing boilers are still the same thing. When we look at those you'll see that, but you can see checking these for continuity is the easiest way to find out whether they're broken or not. Now the last safety device gas control I want to look at in this video is this thing here up on the right hand side of this boiler. Now this is an air pressure switch or fan proving switch. So this is the fan pressure switch. Now how the fan pressure switch works is not what you'd expect it to be. So basically when the boiler switches on, the pump comes on. Then the PCB checks to see if we've got continuity actually at the air pressure switch between our common and our normally closed. Now if it did it between our common and normally open, then we would be able to bridge out the air pressure switch and leave it, which we can't do that because it's a safety device. If you bridge out a safety device, you make that appliance automatically ID in that unsafe situations procedure. So IGMG 11 would deem that immediately dangerous. So what we're going to do is we'll have a close look before we take it out, and then we're going to take it out and then we're going to check it on the bench. Now as you can see, this is our air pressure switch. This black lead here is what went onto the fan. You can see there's also a clear lead which goes out at the back. And that just goes out of the back of the combustion chamber. If we look on the side, you can see there's 3 connections, but there's only 2 wires. So we've got a brown wire going to that connection. We've got nothing on the center wire, on the center connection. And then we've got this blue wire, which goes onto this back connection. So when we take them off, we'll have a look what all these connections are. But one would be common, one would be normally closed, one would be normally open, and then on these 2 connections here, one would be positive, one would be negative. Now let's have a look at this air pressure switch a bit more closely. This one here is our common. So this one had the brown wire connected to it. This one says normally closed. This didn't have any wires connected to it at all, and you can see this says normally open, the NO, which had our blue wire connected to it. So you can now see the different switches. So hopefully I'm going to explain how this works. Now, got a multimeter here, got it set on audible alarm, so when I touch the 2 leads together we should get a noise. So we know that's working. Now then, when you get this out of your van, the first thing you need to do is check we have continuity between the common and the normally closed, which we have straight away. Okay, if you don't have that to start with between the common and the normally closed, then you're wasting your time. So we shouldn't have any continuity between common and normally open, which you can see there isn't, and there shouldn't be anything between these 2, the normally open and normally closed, which there isn't. Now if we look at this tube, I flip it over, you can see it says high there and low there. Okay, now this black tube we know was attached to the fan. So the fan is actually, via the aid of Venturis, sucking the pressure switch open rather than pushing it open. So I told you before we should never be sucking on an air pressure switch, but I've got to do that to show you how it works. So we should have continuity between these 2. And when I suck on the air pressure switch, we should lose continuity between these 2, but gain it between the bottom one and the top one. Okay, so let's have a go at that first. So you can see as I sucked on the tube, we lost continuity. So that side's working. Okay, so now then, what we should do is, when I suck on the tube, is gain continuity between that one and that one. So let's try that. So no continuity at the moment. Ooh, we're not gaining anything. So this air pressure switch is actually not working. So let's prove it on one what I do know is working, which is this is the same air pressure switch. which we have, and between the bottom one and the common. So they're normally open, and the common we should have nothing, which we haven't. So if I suck on the tube, we should lose the continuity here and gain it here. So that part works. Let's try the bottom bit. So you can see that one works perfectly. So just remember, don't test them by sucking on the tube because you could damage the diaphragm. But hopefully that shows you how to test the air pressure switch and what you should be looking for. Now, last few things I want to look at for boilers are, first of all, this. So this is what we call a zero governor gas valve. Now, the multifunctional valve we looked at in part 2, that was an atmospheric burner. So basically when the gas burns with that one, the gas is always trying to go up. And the gas valve is what sets the pressure going to the burner. Slightly different for zero governors. Now, a lot of the new condensing boilers use zero governor gas valves. So the way this one works is, the gas comes in here, and what happens is, it's connected to the back of the fan. So combustion air is drawn in here, and the fan pushes, and well, it kind of sucks the gas in and the air at the same time and blends it in this tube here, and then burns it 360 degrees around this cup burner. There are also downward burners as well, but they kind of work on the same principle. So in this case, the faster the fan is going, the more gas is being drawn into the burner. The slower the fan is running, then the less gas is being burned. Now, inside this zero governor, there is a diaphragm with a very slack spring on it, but that is set for 0 millibars. Okay, so once the pressure goes lower than 0 millibars, so on this outlet test point here, you would actually get a minus figure reading. This is our inlet test point, so that would give us, we don't want that going lower than 17 millibars, but this test point here would give us a 0 reading. So when it goes lower than 0 millibars, it opens and allows the gas in. Now you can see there are 2 solenoid valves here, and what the solenoid valves are there for is, this boiler has to go into a purge before it ignites to get rid of any unburnt gas from the heat exchanger. So these solenoid valves are there to close off the gas flow to the gas valve, to allow the fan to run and draw just fresh air in through these slots here, which will then clear the combustion chamber of unburnt gas so we don't get explosive ignition. Now the other control you can see here, on here, is your ignition flame rectification. But we've got 2 probes here now. Now even some of these boilers still have a separate flame rectification, but it still has ignition. But this one uses the same, it looks like a spark plug, it has a HT lead going onto the ignition cable, but it still uses the same thing, and it uses an earth cable here, so we have to have an earth because the ignition needs an earth to go to ground to make it work. So again, this is sending the AC current, which then turns to DC, and the control part of the PCB knows it's burnt 360 degrees around there. Let's start with the ECV, or emergency control valve. Now, ECV, a couple of things. First of all, it's a gas control. Secondly, we have a handle. Now, if this handle is missing and it's a non-emergency situation, then that would be categorised in the unsafe situations procedure item G11 as at risk. But if there was a smell of gas and there was no handle, that would be ID. Also, if it was inaccessible, same thing applies. Non-emergency at risk, emergency would be ID. Now, this handle cannot fault it on. Okay, this one's faulted it on. So you can see that's off, that's on, that's off. Okay, Now this one does actually come with a little lock on there, so you could actually turn it off and lock it off and it wouldn't fall to on. Okay, so falling to on, sometimes you can spin the handle around and it won't fall to on then, but you wouldn't be putting these in anyway. This would be cadent, so anything wrong with the ECV, then you must contact the emergency service provider, which in our area is cadent. So that's the ECV. After the ECV we have the Anaconda. Okay, now the Anaconda, a couple of things with the Anaconda. It's not a control and it's not a safety device, but it links the ECV to the regulator. Now then, the incoming supply pressure here on a low pressure system is 75 millibars. Okay, but it could also be in a medium pressure up to 2 bar. So this little flexible pipe could be getting a lot of pressure in there. So we have to make sure we protect it if we're soldering near it. Okay, it's made of stainless steel, but flux will rot right the way through it very, very quickly. So we've got to make sure when we're soldering near a meter and we're near an Anaconda that we protect the Anaconda from getting any kind of flux on there, because it will rot through it quite quickly. Just remember, there is up to, on a low pressure, up to 75 millibars coming in there. Medium pressure could be 75 mil to 2 bar. So just watch out for that. Now then, after the Anaconda, connected to that is the regulator. Now what the regulator does is what it says on the tin. It regulates the incoming gas supply to our working pressure at the meter of 21 millibars plus or minus 2 millibars. So that's 19 to 23 millibars. This is regulating the 70, in this case the 75 millibars coming in. So it's an incredibly important part and an important gas control. And again, if this has corrosion on it, but it's not leaking gas, then it would be at risk in the unsafe situations, and if obviously it was leaking gas, then it would be ID. So let's have a closer look at this regulator. So this is what we call a constant pressure type regulator. So what we can see here is this part here is a seal. So I'm going to show you another one in a minute with this removed so I can go through how it works. So if we look at the label on here, it tells us, it gives us 6 meters cubed an hour. So this would go on a G4, U6, E6 meter. Okay, wouldn't be able to go on a G10 or a U16. It gives us, well, its incoming pressure, 75 millibar, and it gives us our normal outlet pressure of 22 millibars. It also said there the metering pressure is equal to 21 millibars, so that's your working pressure. 21 millibars plus or minus the 2 millibars. It also says it's for second family gas, so this can only be used on natural gas, but there are some what say can be used on first, second and third family gases. So if you don't know what the family gases are, first family gas is man-made gas, so that's coal gas. Second family gas is natural gas, and third family gas is LPG. So that's what the regulator label gives you. And again, if this was missing, this would be the responsibility of the ESP, the emergency service provider, to replace that. Now, there is an O-ring what goes on here, and every time you disconnect a gas meter now, you have to replace the O-ring. There's also one at the other end of the Anaconda which goes onto the ECV. Now this little sticker you can see here is your label for the customer to tell them how to turn the ECV on or off. You should be really carrying this tape. So if this is missing, you would put that on. You wouldn't ring Cadent out to put that tape on. So let's see how this works. So this is the same regulator, and I've taken the cap off, so you can see this screw here. So inside here is a diaphragm, there's a spring here. So if I undid this locking screw here and screwed this screw downwards, it would put pressure on the spring, which will put pressure on the diaphragm, which would increase the pressure coming. Well, this is where the inlet comes in, this is where the outlet comes out. So it would give you a greater pressure on the outlet. Now if I decrease this, so if I screwed it upwards, okay, so anti-clockwise, so if we're looking at this way, I'll be screwing it anti-clockwise, then it would decrease the pressure coming out of here. But remember, we are not allowed to play around with this. Only ESP or somebody working for our ESP would be allowed to adjust this. So this would give us a standing pressure. So with all our appliances turned off, we would be looking for a standing pressure of between 19 and 29 millibars. You don't want any more than 29 millibars because it could blow your water out of a U gauge, because a U gauge only goes up to 30 millibars. Now and again, our working pressure would be 21 millibars plus or minus 2 millibars. So you would put your appliances on and make sure that your working pressure at the test nipple of the gas meter would be between 19 and 23. So that's a quick look at this regulator. Now this is a slightly different regulator. This is what we call a medium pressure regulator. So you can see here, it says second family gases. It says its maximum operating pressure, or its MOP, is 2 bar, and its normal working pressure is 22 millibars. So this is a natural gas one, not an LPG one. And if we look at the side here, we've got this UPSO valve, which is an under pressure valve. So LPG regulators have OPSO and UPSO, so over pressure shut off, which is in here, and under pressure, which is here. So that's a different regulator. So the incoming supply here would be 75 millibars to 2 bar, and then its outlet pressure here would be 21 millibars plus or minus 2. Now I might do a full video on tightness testing with medium pressure, so that'll help you to understand that a little bit more. But that's the difference between the medium pressure and the low pressure. Is the medium pressure has this little UPSO valve, which we need to use if the pressure drops. Resets the diaphragm and the regulator. So that's the medium pressure. And that is the end of this video. So if you've liked this video, why don't you give us that thumbs up, because it lets me know you care, or leave a constructive comment down below. If you've not subscribed to our YouTube channel yet, why the hell not? Get subscribing, because you won't regret it. And don't forget to hit that notification bell, because I release videos every Wednesday. As usual, all I've got left to say is thanks for listening, thanks for watching. I look forward to seeing you again next Wednesday. Cheers guys.